2.2, shh, please be discreet. So this is all word problems in order to implement everything that we did in 2.1. So the Library of Congress in Washington, D.C. is considered the largest library in the world. They often receive boxes of books to be added to their collection. Since books can be quite heavy, they aren't shipped in big boxes. On average, each box contains about 8 books. How many books are received by the library? In 6 boxes, 10 boxes, or in boxes. So we have to create a table, a graph, and an equation to model the situation. So we're going to start with a table. So we know that there's boxes of books. So we have boxes and books. The number of books depends on how many boxes are received. So if there's 0 boxes received, there's 0 books. If there's 1 box, there's about 8 books. 2 boxes, 8 more books. So every box contains an additional 8 books, which lets us know that this is linear. Now, when we're talking about boxes, if you receive a box that's half full, it's still a box. So because we're not going to have any partial boxes, no 0.75 of a box, this is going to be a discrete function. So as we keep on going, 3 would be 24, 4 would be 32 books. So now we need an equation. So we have y equals mx plus b, for m for how it's moving, your rate of change, and b for where it begins. So your rate of change in this one is that plus 8 that's happening. And your beginning amount is 0. So we don't have to add 0 onto the end because it's not going to change anything. So when we go to graph this on the x-axis, we're going to put our boxes, and on the y-axis, we're going to put our books. I made my y-axis go up by 5s because my rate of change is going up by 8s, and I wanted to include as much of this as possible. So we know that this is discrete, so there's just going to be a bunch of dots on the graph. So at 0 boxes, 0 books. 1 box, 8 books. Then 16, then 24, and then 32, and 40, and 48. And we leave it just like that. Now the domain is the x values. So when we're talking about domain, there we go. When we're talking about domain, we're talking about the x values of a function, all of your input values. Now, if we were talking about a range of numbers, if we said from 0 to 6, that includes every number from 0 to 6, even 0.0003. We already talked about the fact that the boxes can only be your whole numbers, 1, 2, 3, 4, 5, 6. So the domain of this function is the list of those values. We have 1 box, 2 boxes, 3 boxes, 4 boxes, etc. And we put them in those funky, curly, curvy brackets because it's a discrete function. All discrete functions go in those brackets because it's a dot here, a dot here, a dot here. And you have to list out those values for where the dots lie. So these are also called natural numbers or counting numbers. Because when you count, 1, 2, 3, 4. So our next situation says many of the books at the Library of Congress are electronic. If about 13 books can be downloaded onto the computer each hour, how many ebooks can be added to the library in 3 hours, 5 hours, or in hours? So the first thing we notice is that we're talking about 13 books downloaded each hour. So because most of you have downloaded an app before in your life, you know that when you're downloading, it's constantly downloading. From the time it starts downloading to the time it stops downloading, you could check it at any point in time and see how much of that percentage has downloaded. So we have hours and ebooks. So at hour 0, there were 0 ebooks. At hour 1, since it's 13 per hour, it puts us at 13. And then at hour 2, there's 26 because each hour it's an additional 13. Hour 3, it's 39. Hour 4, it's 52. So because we're adding, this is linear. And because you could check how much percent has downloaded at any point in time. So at 30 minutes, you could look and see how much is downloaded. After an hour and 15 minutes and 2 seconds, you could look and see how many books are downloaded. So that makes this continuous, because at any point in time, you could check how many boxes have been how many books have been downloaded. So when we write our equation, we have y equals m is how your numbers move, that rate of change, which is 13. Your rate of change is always touching x, and then our beginning amount is 0, so again, we don't have to write it. So the next thing to do is label your graph. I'm going to label it pretty much the same as the last one, except my y values are going to go up by tens. So when we go to put our dots, we know that we're eventually going to connect them because it's continuous. So when we plug in each of our values, 0 books at 0 minutes, 13 books at 1, 26 at 2, 39 at 3, 52 at 4, 65 at 5, 78 at 6, at 7 would be 91, and 8 would be 104. So that's off the grid. So we connect these next because it's continuous. So if you look at your graph, and this is just me doing extra, at 2.5 hours, there would be approximately 30 books downloaded. So at 6.5 hours, we would have approximately 85 books downloaded, just under 85. So at any point in time, you could stop and check how many books have been downloaded. So it's continuous. So the domain of the function. So because it starts at 0 and it includes every number after 0, because we're assuming that there's unlimited space. So starting at 0, those books, 0 hours, those books start downloading, and they download all the way to infinity because we're assuming there's not a limited amount of space. So because it can be at 0 hours, we put a hard bracket because it stops at 0, and we put a parenthesis around infinity because it doesn't ever reach infinity. Another way you could write it is that all of your x values are greater than or equal to 0. Moving right along. Question number 3 says, the librarians work hard to keep the library orderly and put books back into their proper places after they've been used. If a librarian can sort and shelve 3 books per minute, how many books does that librarian take care of in 3, and we're changing this one. So it says in 3 hours. We're going to change hours to minutes. 5 minutes. Or in minutes. So because this one is very much like the ones on the front page, I'm not going to walk you guys through this. I want you guys using this as an opportunity to practice this one and then check your answer for it on Canvas. The next several questions are comparisons. So would it make sense in any situation for there to be 32.5 books? Now, we've talked about with shipping, you're not shipping half of a book. With downloading, you can have half of a book because it's progressive, it's gradually downloading. And half of a book on a shelf? Nope, we don't do that one either. The book is either on the shelf or not on the shelf. So you can download 32.5 books. So we've also went over continuous versus discrete as we did these problems. So you should be able to answer that one on your own as well. So we're going to flip over to question number 6. It says a giant piece of paper is cut into 3 equal pieces, and then each of those is cut into 3 equal pieces, and so forth. How many papers will there be after a round of 10 cuts, 20 cuts, in cuts? So when there's 0 cuts, there is 1 sheet of paper, 1 piece of paper. When there's 1 round of cuts, so they've cut it here and they've cut it here. So now there's 3 pieces of paper. When they've cut again, so it's that second round of cuts, they cut each of those into 3 pieces. So now we're up to 9 pieces. So when we look at a table of these values, we're going to call this cuts or rounds of cuts, really. So we have rounds of cuts and pieces of paper. So at 0 cuts, there was 1 piece of paper. At 1 cut, there were 3 pieces of paper. At 2 cuts, there was 9 pieces of paper. So if we look for our rate of change at this point, we notice that we're multiplying, because the only way to get from a 1 to a 3 to a 9 is through multiplication. So we're multiplying by 3, and that lets us know that this one is exponential. So if we continue the pattern, we have 27, and then at 4 would be 81. So if we were to write this equation, we would have y equals a times b to the x. That's your exponential equation, a times b to the x, where a is your 0 amount, your y-intercept, which is 0, 1. And then b is your multiplier, which is that 3. So when we plug in what we know, we have y equals a is 1, b is the multiplier 3, x in the exponent for exponential. We've already answered this question in turn 2. So that 1 isn't quite necessary because anything times 1 is itself. So we could also rewrite this as y equals 3 to the x, and that x must be in the exponent. Now, if you are cutting sheets of paper, if you cut halfway through a sheet of paper, it's still 1 piece of paper. It just has a cut in it. So this is a discrete function because you have to cut all the way through that paper before there's multiple pieces. So you have to have that 1 round of cut, 2 rounds of cuts, 3 rounds of cuts. So this is discrete. Because half values on the rounds of cuts don't make sense. So we're going to set up our graph. So now that we have our table set up, we can go ahead and graph everything. So at 0 rounds of cuts, there was 1 sheet of paper. At 1 round of cut, there were 3 sheets. At 2, there were 9. At 3, there was 27. At 4, there was 81. And we're off the grid. So because this is discrete, our domain is going to be in the curly brackets, and we list the x values, which is domain as x values. We list the x values that make sense. So we have 0 cuts, 1 cut, 2 cuts, 3 cuts, etc. So would it make sense to look at the number of pieces of paper at 5.2 cuts? No. If you don't cut all the way through a sheet of paper, it's still a sheet of paper. So cannot have or cannot cut 0.2 times. So if you cut a fifth of the way through the piece of paper, 0.2 times, it's not going to create a new piece of paper. So would it make sense to look for the number of cuts it takes to make 53.6 papers? No. Cannot have 0.6 papers because we're talking about how many pieces of paper there is. So if you cut it, it's a whole piece. And on to the last problem. Medicine taken by a patient breaks down in the patient's bloodstream and dissipates, that means goes away, out of the patient's system. Suppose that a dose of 60 milligrams of an anti-parasite medicine is given to a dog, and the medicine breaks down such that 20% of the medicine becomes ineffective every hour. How much of the 60 milligram dose is still active in the dog's bloodstream after 3 hours, 4.25 hours, and in hours? So we're going to be comparing hours to milligrams. So at 0 hours, there was 60 milligrams. So at this point, I want to pause and write the equation because that's going to make things easier. Because we're doing 20% of it, we know it's going to be exponential. So when we write this, we have y equals your zero amount, that y-intercept is 60. Now, when it comes to these milligrams, at the very beginning, and the way you need to think about these percentages, at the very beginning, that dog had 100% of the medicine in its system. And then it dissipated, it went away at a rate of 20%. So when we finish writing this, we have y equals 60 times 100 minus 100% minus 20% is 80%. But we don't ever put percents in an equation, so we need to rewrite it as a decimal. So we have 60 times 0.8, 0.80, same thing, with the x and the exponent. So now you can use that equation to fill in the rest of your table. So after 1 hour, that dog now has 48 milligrams of the medicine. After 2 hours, the dog has 38.4 milligrams left in its system. After 3 hours, the dog has 30.72 milligrams of that medicine left in its system. And in 4 hours, we're at 24.576 milligrams of medicine. So the next thing we need to do is decide, is this continuous or discrete? So because the medicine is it's gradually dissipating out of this dog's system. It's not that it waits till the end of the hour and just poof, 20% of it disappears. It's gradually coming out of that dog's system, so therefore it is continuous. So that means the dots on our graph will be connected. So next we need to do is set up the graph. So as we plot these points, we have 0, 60 milligrams of that medicine in the dog system in the very beginning. After 1 hour, there was 48 milligrams. After 2, there was 38.4. After 3, there was approximately 30. After 4, there was 24. If we continue down our table using a calculator or however, we end up at 19.6, and then 15.7, and 12.6, and then it comes down to 10 and some change, and 8 and some change, and 6 and a decimal. And we can connect our lines to make that curve. So we already answered the question. It's exponential. The domain is not specific values, it's a range of values. And that range of values starts at 0 when we first administer that medicine to the dog, and then it continues until it's completely out of the dog's system. And we don't know when that is, so we just put infinity. So would it make sense to look for when there's 35 milligrams of medicine? Yes. And that's because the medicine, I'm going to put meds, the meds gradually decrease. So it says, would it make sense to look for an amount of medicine active, an amount of active medicine at 3.8 hours? And it's the same thing. Yes, because the meds gradually decrease. It's not all at one point in time. So then you can do the compare and contrast, and you can do the discrete and continuous because it's something we've already discussed. But when it's discrete and continuous, I have a note here that says, ask yourself, does whatever's going on happen all at once or gradually? That's what you need to consider when you're deciding discrete or continuous. Is it something that happens like boom, all at once? Or is it something that slowly happens across a span of time? All right, and number 10 is asking for differences. You guys can come up with differences that you notice in each of the representations in each of the problems, and then check yourself on Canvas.